In this section, we'll be looking at vertical stretches and compressions. This is going to occur when we make our y values bigger or smaller than the previous graph. Let's see a picture of what a vertical stretch or compression would look like. Again, we have our xy plane, and let this red graph be our f of x here. If we wanted to vertically stretch this graph, then we would obtain a graph that looks something similar to what we see in the blue graph here. While this looks very similar to a vertical shift, there's a key difference here. And the key difference is that the y values haven't been changed uniformly. So for example here, the distance from our two graphs might be, let's say, 2, but the distance from here to a point over here, maybe it's 10. So what's happening is that our y values are no longer being changed by a uniform amount. So we're not adding anything this time. But this time our y values are being multiplied by a uniform amount. And so this is how we're stretching our y values, or how we're shrinking them. Again, if our red function is f of x, then to vertically stretch or compress this, what we're going to do is we're going to multiply f of x by some constant c here. Let's summarize this on the next page. A vertical stretch of our function f of x is given by g of x, which is equal to c times f of x, where c is greater than 1. Let me go ahead and copy the same thing for a vertical compression. Here we have that a vertical compression of our function f of x is again given by f of x times some constant c, where c is between 0 and 1. Okay, let's go ahead and look at an example. Example 5. Go ahead and sketch the following graph. In this case, we're looking at f of x, which is equal to 1/2 times x cubed. In this example, let's go ahead and sketch the graph of f of x, and we'll also sketch the graph of x cubed. First, let's go ahead and just input some points here. For our first points, we'll be looking at input values of x, and our output values are going to be given by x cubed. And let's just go ahead and look at -2, -1, 0, 1, and 2. So plugging these inputs into x cubed, what we're going to get out is the following. So these are our outputs. Now let's go ahead and look at our function f of x here. Again, our x values are our inputs. And we want to look at -2, -1, 0, 1, and 2. Then the outputs are going to be -4, -1/2, 0, 1/2, and 4. Let's go ahead and draw both of these graphs. In our original graph, f of x, y is equal to x cubed, our function looks like the following. After we applied our transformation of 1/2 times our function, we're going to get the function that was given to us in example 5. And let's let f of x this time be given by red. What we see is that all the y values in our f of x graph are going to be less than the y values in our blue graph. And so f of x is going to look something like this.